Signal intensity in proton NMR. So in proton NMR, every hydrogen in a molecule will give us a signal. And the number of distinct signals depend on the number of hydrogen with a distinct chemical environment. If we were to have two hydrogen in a molecule with the same chemical environment, meaning they connected to the similar atom and overall look exactly the same, then those two hydrogen will give us the same signal, thus raise up the intensity of that signal. So if the signal of two hydrogen are exactly the same in both chemical shape and multiplicity, then that signal is then twice the intensity compared to another signal. And the intensity of the signal is normally the area of the signal, because in proton NMR we will get a signal, and the intensity of the signal is basically the area under the curve of the signal. Therefore, we also refer to this as an integration number, because to find that area, we have to integrate what is the area under the curve. For an example, let's say we have this molecule. So here in this case right here, how many distinct signals would we expect to see for this molecule? So the answer, it would be 3. Why 3? So here in this case right here, overall we would expect to see there's 7 signals all total, because there's 7 hydrogen in this molecule. However, they show up as 3 distinct signals. And the reason is as follows. These two hydrogen right here are chemically similar. The reason is because they're the same distance to this bromine, and they're exactly the same thing. So therefore, we would expect to see one signal that it consists of these two hydrogen. So in this case right here, these two hydrogen right here will give us one signal, and the intensity of the signal from these two hydrogen will be twice compared to another signal that they make up of one hydrogen. And next, for this hydrogen right here, these two hydrogen right here are chemically equivalent as well. And the reason why is they look symmetrical. There are plenty of symmetry in them. And these two hydrogen are basically exactly the same thing. So therefore, it will give us another distinct signal. So let's say this is signal B, and the previous one, that was signal A. And lastly, these 3 hydrogen right here from this methyl group, due to the rotation of this carbon-carbon single bond, these 3 hydrogen will be chemically equivalent, and therefore they will give us another signal. And this signal is made up of 3 hydrogen, so its ratio with respect to another signal would then be 3 times. And let's now call this signal C. So let's write a few things. Signal A with an equal to 2 times the intensity, because there's 2 hydrogen that make up that signal. And signal B would also be twice the intensity as well. And signal C will be 3 times the intensity. Then there are 3 hydrogen that make up the signal C. So therefore, again, we would then see there are 3 distinct signals for this molecule that we would expect to see in proton NMR. Let's now try another example. How many distinct signals would we expect to see for this molecule below? And the answer would be 2 distinct signals. Again, in this molecule right here, it has up to 7 hydrogen, so therefore we will see 7 signals. However, many of the signals may be the same. So here in this case right here, there's 3 hydrogen. Again, because due to the rotation of this carbon-carbon single bond, it can rotate, and therefore these 3 hydrogen would appear to be chemically similar. And now let's call this signal A. The other 3 hydrogen from the other methyl group are also exactly the same thing as well, due to symmetry. And they will give us another signal. And in this case, this 6 hydrogen will be the same signal A. And lastly, we would expect to see another distinct signal for this hydrogen in here. And that would be our signal B. So therefore, we would expect to see two signals. There are 7 signals altogether, but 2 distinct signals. Signal A would be 6 times the intensity, and signal B would then be 1 time the intensity. So if we were to compare the intensity of the signal from the hydrogen A and the hydrogen B, then the ratio will be 1 to 6 in terms of ratio. Let's now try a few more practice problems. How many sets of equivalent protons, and what are the intensity of each of the signal that we would expect to see for this following molecule? Let's first try molecule, the first one. How many distinct signal would we expect to see? So in this case, it would be 3. And the reason why is, again, this 3 hydrogen in here, in this methyl group, will give us 1 distinct signal. Let's call this signal A. And because there are 3 hydrogen that make up signal, so therefore the intensity of this signal will be 3 times. Moving on, these 2 hydrogen in here are chemically similar, so therefore they will give us another distinct signal. And now let's call this signal B. And because signal B, it comes from 2 hydrogen, so therefore it will be twice the intensity. And lastly, this methyl group. This methyl group is different compared to the methyl group that we've seen on that make up the signal A. And the reason why is because this methyl group is connected to an oxygen, while this methyl group over here is connected to a carbon. So therefore, they are different. And this will give us another signal. And this will be the signal C. And signal C will then have 3 times the intensity. So those are the amount of signals and the intensity of the signal that we would expect to see for this molecule. Let's now try another example. On this one, how many distinct signals would we expect to see? And the answer would be 2. So here in this case, we can see that there is a plane of symmetry here in this molecule. And because of this plane of symmetry, it makes this hydrogen and this hydrogen exactly the same thing. So therefore, these 2 hydrogen will give us 1 signal. And now let's call this signal A. And signal A will then be 2 times the intensity, because there are 2 hydrogen make up that signal. And we would expect to see another distinct signal coming from this 2 methyl group. These 2 methyl groups are exactly the same thing. The hydrogen in them are chemically equivalent. So therefore, this will give us another distinct signal. And let's say this is signal B. And signal B will then be 6 times the intensity. So signal B will be very big compared to signal A, because the ratio will be 6 to 2. Let's now move on to this next problem. How many distinct signals would we expect to see for this molecule? And the answer would be 3. 3 distinct signals. This hydrogen is different than this hydrogen, and this hydrogen is different than this hydrogen because of their proximity to the bromine. This one hydrogen is connected to the same carbon they're connected to the bromine, so therefore it will be different compared to the hydrogen from another carbon. So here in this case, we would expect to see signal A from this hydrogen, and it will be 1 time the intensity, since there's only 1 hydrogen making up the signal. And we will expect to see a different signal for this hydrogen. Let's now call this signal B, and signal B will be 1 times the intensity. And this hydrogen will be the signal C, and 1 time the intensity as well. So therefore, we would expect to see 3 distinct signals for this molecule. Now notice hydrogen B and hydrogen C are not the same thing. Again, because of their proximity to the bromine. This hydrogen is much closer to this bromine compared to this hydrogen. So therefore, they can't be the same. Let's now move on to this next problem. how many distinct signals would we expect to see for this molecule? First, we will see one signal from this methyl group. So that will be distinct. So now let's call this signal A, and that will be the 3 times the intensity. And in this carbon in here, there are 2 hydrogen in here. And these 2 hydrogen will give us a distinct signal compared to the signal A. And now let's call this the signal B. And there are 2 hydrogen in here. So therefore, it will be twice the intensity. And the other one, we actually form this hydrogen in here. There's a hydrogen in here, and it will be a unique signal compared to A and B that we have seen already. So this will be signal C, and that will be the 1 times the intensity. And lastly, these 2 methyl groups are actually identical. And the reason why is because of rotation around this carbon-carbon single bond. It can rotate around and therefore make these 2 methyl groups similar. So we would expect to see another signal for this 2 methyl group, and that would be the signal D. And signal D would then be 6 times the intensity compared to the other signal. Let's now try a few more problems. So for this next molecule, how many distinct signals would we expect to see? And the answer, 2. This methyl and this methyl are the same. And it's easy to see that because there is a plane of symmetry in here. So therefore, we would expect to see 1 signal from this 2 methyl group. And now let's call that signal A. And that would then be 6 times the intensity. This 2 methyl group, the 2 CH2 in here will give us another same signal as well. And the reason why the hydrogen in here are the same is because they're connected to a methyl and a carbonyl. Same thing as the hydrogen over here on the other side. It is connected to a methyl and a carbonyl. So therefore, they're exactly the same thing. So we will expect to see another signal. Let's now call this signal B. And this signal B will have 4 times the intensity. And let's now try a few more examples. How many distinct signals would we expect to see for this molecule? So here in this case, we would expect to see 1 signal for this hydrogen. So let's call this signal A with 1 time the intensity. Another signal from this methyl group. So let's call this signal B, and signal B will be 3 times the intensity. And now, there's hydrogen in here on this benzene ring. These 2 hydrogen right here are the same. And the reason why, again, is there is symmetry bisecting this molecule. And when we reflect them through that mirror plane, they will be the same thing. So in this case, these 2 hydrogen will give us 1 signal. And now let's call that signal C, and that will be 2 times the intensity. And for the same logic, these 2 hydrogen right here will be the same as well. And they will give us 1 similar signal, and this will be the signal D with 2 times the intensity. Let's now try this molecule. This is actually a unique problem because now we are having a molecule that have a chiral center in it. So here in this case right here, how many distinct signals would we expect to see? And the answer, actually quite a few. So first, this methyl group right here will give us 1 distinct signal. So let's call that signal A with 3 times the intensity. This hydrogen over here will give us another signal, and let's call this signal B with 1 times the intensity. The 3 methyl group in here are the same, and that will be signal C with 3 times the intensity. There will be another signal in here, and that will be signal D with 1 times the intensity. And now, the exciting part. There are 2 hydrogen in here. Are these 2 hydrogen chemically equivalent? And the answer, no, they are not chemically equivalent, but then they are different. And the reason why is as follows. One of these hydrogen is pointing in the same side as the hydroxy group because both of them are wedged. And versus the other hydrogen is dashed, so it's on a different side. So therefore, these two hydrogen right here would not be chemically equivalent because they are not at the same proximity to this hydroxy group over here. So in this case, we would expect to see one distinct signal for this hydrogen, and let's call this signal E with 1 time the intensity. And this hydrogen over here, signal F with 1 time the intensity. So the two hydrogen in here are actually not chemically similar, thus giving us distinct signal. However, the 3 hydrogen in here are chemically similar, and the reason why is due to rotation of this carbon-carbon single bond. They can rotate around and be the same. But in the rotation on this bond right here, these two hydrogen right here would always be different regardless of the rotation.